This last section of Chapter 3 is a little bit of a tangent from everything that we've been doing so far in this chapter. In this section, we are going to use derivatives as a method of approximation of a function. Let's look back at the definition of the derivative. It said that the derivative of a function was equal to the limit as some delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And the idea was that if we had our graph, we have some point on our graph, this gives us the slope of the tangent line. Essentially saying that if we have our x value here, and then we move off of our x value by a small amount, we add delta x to it, or we could go the opposite direction and subtract if we wanted to. We're comparing this point here at x and its y value of f of x to the y value at x plus delta x. And that's not exactly the point on the line. The point on the line will be a slightly different point, but it is an approximation for that particular point. The point on the line, which is a lot easier to do once you have this tangent line, is an approximation for this actual value of the function. In other words, you can say that if we're off by a little bit of delta x, then the answer is off by a corresponding delta y. Excuse me, the delta y is between f of x and f of x plus delta x. This one here. Essentially, delta y is this difference on top. It's the difference between the y value of the point that we started with the y value of the point that we ended with. We always put the last one first minus the first one. Well, we can rephrase our limit definition as, remember, we have a different notation, the dy over dx, that stands for a derivative. And this is going to be the limit as delta x goes to 0 of the top is just this delta y, and the bottom, of course, is still delta x. Essentially, the point of this notation here is that even though the derivative itself is not actually a fraction, it does approximate one. It approximates the fraction delta y over delta x, where those are legitimately distances in our graph. And the point here is that we can go ahead and use this as a way to approximate the values of the function. We're going to do that by introducing a new term, the differential. The differential, we basically treat dy dx as a fraction. We're kind of breaking that rule, but it will actually be helpful to do that. If we set dy dx is equal to that's our derivative, then we can essentially multiply this by delta x and say that dy is equal to the derivative of f at x times dx. We can say dx is the differential of x. It's not really an approximation of how much x changes, because usually what we're going to do is say that delta x is dx. But then dy is going to be an approximation for this delta y. In our actual picture here, it is actually the distance between our initial point here and the point on the line above x plus delta x. This is what dy is. And so what we're saying by trying to say that this is an approximation, we're basically going to be able to calculate dy using the derivative and use that as an approximation for what delta y is. Because delta y is actually going to tell us about the original function. These are close enough in practice that this is very helpful. Or in other words, what we can basically say here is that delta y is approximately dy, or since delta y is actually this expression here, we can even say that f plus x plus delta x, remember this delta x and the dx are the same thing. This is not equal to, but approximately equal to f of x plus dy. So if we want the value of the function at this new point that's close to the original point, then all we need to do is take the y value at the original point plus this little change in our y value. That's the idea here. My favorite example of using this idea is the square root. Let's take something like the square root of 50. Since 50 is not the square of another number, its square root is some irrational number, and it's probably not something anybody's memorized. So of course, we could just go ahead and reach for a calculator, but can we get a good approximation of this square root without a calculator? Well, the first thing we can notice is that 50 is quite close to 49, and 49 is in fact a perfect square. The square root of 49 is 7. We're going to use this 49 as our starting point, our x. Say x is 49. And then we have a function, f of x, which is just the square root function. Which, since we're going to be taking derivatives here, we remember that the square root function is just x to the 1/2 power. We're going to make a slight change in our x value, going from 49 to 50, and that's going to give us a delta x. We always take our final number, this 50, minus the 49. Of course, that difference is just 1. And that's also going to be our dx. So you can think of these as the same thing. There's a different idea lying behind both of them. That's why they have different notations. But in these problems, we want to just think they're the same kind of thing. Now that I've done that, I can go ahead and look at what my differential is. Remember, I'm just taking dy is equal to the derivative times dx. So I am going to have to take the derivative of my function. What is the derivative of x to the 1/2 power? Well, it's just 1/2 times x to the negative 1/2 power. Because, well, 1/2 minus 1 is negative 1/2. Now, I do want to actually go ahead and turn this back into a square root, so that I can plug numbers into it better. So x to the negative 1/2, that means we have an x to the 1/2 on the bottom, and x to the 1/2 we already know is the square root of x. So this is the same thing as 1 over 2 times the square root of x times dx. That is our differential of the square root function. So in our particular case right here, where we said x was 49 and dx was 1, then we're saying that dy is equal to 1 over 2 square root of 49 times 1. Or in other words, since the square root of 49 is 7, we have 1 over 14. And this is just saying that the square root of 50 is going to be approximately the square root of 49 plus our dy value. Square root of 49 was 7, and our dy we just found was 1 over 14. And this is, if you want to, we could actually use long division to get the decimal version of this. This is equal to 7.0714 and so on. Now, how close did we actually get? We know how to find the square root of 50 using a calculator. So if we go ahead and just do that, our calculator tells us that the square root of 50 is exactly 7.071067 and so on. So notice here that we got a pretty good approximation. We were correct for those first 3 decimal places. 7.071 is as close as the calculator is going to give us anyways. We could have just used those first four numbers here, and we'd be as accurate as if we'd used the calculator anyways. That's a relatively easy way of getting a very close approximation to this particular square root. And in fact, now that we have our differential, we already have our differential calculated out. We could use this same formula to do mini approximations. Just kind of doing a few quick ones. We know that 80 is close to 81. The square root of 81 is 9. And this time our dx is equal to, now we take our final one minus our initial one. This is the x value we want to plug into it. This time our dx is negative 1. There's no problem with having a negative dx. We can approximate on either side of a particular x value. Our dy, remember, we take 1 over the 2 times the square root of x, in this case is 81, times our dx, that's a negative 1. We get a negative 1 over 18, because we know that square root of 81. That means that the square root of 80 is approximately equal to square root of 81, which is 9, plus our dy. Well, dy is a negative, so minus 1 over 18, which is 8.944, and so on. Actually, it's repeating 4s at that point. Of course, the square root of 80 is exactly, by using a calculator, 8.94427, and so on. Again, our first 3 decimal places are exactly correct. And we're only off by actually less than 2 for the remainder of it. Because 27 versus 44, that's less than 20. You do something like, keep moving up in number, let's say 1300. 1300, if we wanted to find the square root of this thing, we have to think about what are perfect squares that are close to this number. Well, there is a perfect square that is really close. That's 1296, which is the square of 36. If we want to see how far apart these are, or if we want to take the square root of this by using how far apart those are, of course, in this case, we're taking our final minus our initial. So the difference in our values here is just 4. We use our formula. Dy is 1 over 2 times the square root of our initial value here, our x value, times dx. So this is 1 over 2 times 36, but we're also multiplying by 4. We can go ahead and cancel out the parts of the 4. So one of the 2's cancels out that 2. The other 2 cancels out one from the 36. We end up with a 1 over 18, which basically means that the square root of 1300 is approximately equal to the square root of 1296, which is 36, plus dy, which is 1 over 18, and that is 36.055, and so on. It's repeating 5s after that. Actually, maybe I should actually even include a few more. Let's include a few more 5s. Because the actual calculator answer for the square root of 1300 is 36.055512, and so on. We actually got 4 decimal places of accuracy. It turns out in the particular case of the square root, because the square root is concave down, its derivative is not increasing very much as we go up. It's kind of leveling out as we go up. These approximations actually get better and better the higher the x value is. That's not always the case for all functions, of course. The square root is actually going to be more, or the square function is actually going to be more accurate for smaller numbers. Let's do one more example of this. So all the examples I've done so far are, we were pretty close to a perfect square already, so we got a pretty good approximation. What if we were not that close? What if we're looking at 2,000? Now, of course, might want to have like a table of squares available to you to kind of see what is the closest one to it. But the closest square is 2025. This is the square of 45. That's not really that close. We have a dx this time of 2000, or final, minus 2025, which is negative 25. We're off by 25 this time. How much is that going to throw off our approximation? Because obviously, if we're closer to being at a perfect square, our approximation should be even closer. The smaller this dx is, the better our approximation should be. But that doesn't mean we can't try it. Remember, our dy was 1 over 2 times the square root of x, or x in this particular case being 2025, times our dx, which is negative 25. Of course, we get to go ahead and put the square root here is 45. We have 2 times 45, but we also have a negative 25 on top. I'm actually going to go ahead and cancel a 5 from here and a 5 from here. And we end up getting a negative 5 over 18, because what was left was 2 times 9. And that means that according to this, the square root of 2000 is approximately equal to the square root of 2025, which is 45, plus this dy, which of course is a negative 5/18. And if we work that out, we get 0.722 twos repeating. Well, the calculator answer for what the square root of 2000 is exactly 44.721359. So we're not quite as accurate as we were on the previous one. The previous one we had 4 correct decimal places. Here we only have 2. And almost 3. 1-3 is not too far off from 2 at the end. And that was in a case where we were actually pretty far away in terms of x values. We were still pretty close. In fact, there's other ways of approximating the square root that this actually will take a few iterations of those approximation methods to even get quite so close. So the point here is that we are able to do some pretty good approximations using the derivative, using this concept of the differential. Let's look at a few problems from the book that involve this differential concept. Specifically, let's start with problem 3. In problem 3, they give us a function, f of x is equal to x to the fourth plus 3. They give us a particular x value. They say x is negative 2. And they give us a particular delta x, or dx, they actually label it as both, of 0.01. So what is the idea that's going on here? Well, if we start at negative 2, and we change by this delta x, this negative 0.01, we're looking at the number negative 2.01, because we're just adding those two together. And essentially they're asking us to approximate f of negative 0.01, or sorry, negative 2.01. And we're going to use that both. We're both going to use differentials to approximate this, and we're also going to go ahead and plug into a calculator just to check our answer. So, first we need to find the differential. Remember, the differential, we take dy is equal to the derivative. What is the derivative of x to the fourth plus 3? Well, simply 3x. It's 4x cubed, and then plus 0. The 3 goes away. And this derivative, we're then going to multiply by dx. This is our differential. Now we're going to use the numbers that were given to us. We have x is negative 2, dx is negative 0.01. So dy for this particular case is 4 times negative 2 cubed. Thank you, Windows. I definitely need to know that. Times the dx of negative 0.01. And we get to work out what this is. So, well, first things first, negative 2 cubed is negative 8. The negatives are actually going to go ahead and cancel themselves out. We have negative 8, or, well, now positive 8 times 4. 4 times 8 is 32. And so 32 times the 0.01 that we have there is 0.32. That means that f of negative 2.01 is going to be approximately f of negative 2 plus this dy. F of negative 2, well, if we plug negative 2 into our original function, we have negative 2 to the 4th power. Well, the 4th power gets rid of the negative, so what is 2 to the 4th power? That's a 16. 16 plus 3 is 19. And we're going to add 0.32 to that. Of course, that's pretty easy to add. 19.32 is an approximation for what f of negative 2.01 should be. Now, we can go ahead and actually calculate what this should be. We know how to actually take the 4th power, so negative 2.01 to the 4th power, then plus 3. I went ahead and used a calculator here, and I got an exact answer of 19.32240,801. That's actually perfectly exact. There's nothing after that. But the point here is that this sum at the end can be insignificant in a lot of cases, and especially in a lot of applications, where maybe errors in measurement might as well make that meaningless. And so we're basically saying that we've got a very good approximation of our function, and with maybe relatively less work. It really depends on what the function is. Maybe it'd actually be easier just to take the 4th power than it was to take the derivative. Though, I mean, taking the derivative of x to the 4th wasn't too bad anyways. So exactly whether or not this is a good saving you some work might be questionable, but the result really isn't. This is actually a pretty good approximation. It's not far off by a lot. So another problem. Let's look at problem 21. Now in problem 21, they are simply asking for the differential. We're not actually going to do an approximation this time. We're given a function, y is equal to 5x cubed minus 6x. We're asked, what is the differential of this function? Of course, we're trying to find out we need to take the derivative of this thing. The derivative of this is 15x squared minus 6. Hopefully by this point I don't have to explain how we got to that. And that means that dy is this derivative. And I'm going to put parentheses around it just because the entire thing needs to be multiplied by dx. And that's the answer. This is the differential of this original function. And if we need to do any sort of approximation, this is what we could come to. Let's do 25 with the same directions here, but our function is now y is equal to the square root of 9 minus x squared. I want to take the differential of this, which means that I do need to differentiate it. So it might be helpful to remember that the square root is a 1/2 power, and that we need to take the chain rule. So y prime this time, I have something to the 1/2 power. I know how to differentiate the 1/2 power of something. We take down that power to 1/2. We change the power by subtracting 1 from it. But now we need to put that same thing inside. And now we also need to multiply by what the derivative of the inside is. The derivative of 9 minus x squared is a negative 2x. So I'm actually even going to go ahead and simplify this a little bit. I can go ahead and cancel out those 2's. So the 1/2 goes away. I have a negative x, and this thing to the negative 1/2 power, that's really a square root on the bottom. So I'm going to put the negative x on top, and I'm going to put this square root on the bottom. Now, we could get away with not simplifying it like that, but I do like this form a lot better than this one. So our differential, our dy, is this derivative times dx, and why not just put the dx up on top? We're treating dx as just some number that's being multiplied in here. So we can go ahead and stick it on top. That is our differential. And that's what we could use for any sort of approximations. Let's do a word problem next. So the whole point here of being able to do approximations is to do any sort of word problem type thing where we may not know exactly what's going on, but we can use derivatives to get a pretty good idea. In problem 39, this is labeled marginal analysis because that's what we're doing. Remember, in business, when we talk about the derivative with respect to the number of units, we call those the marginals. In this particular case, we're going to be working with the marginal revenue. A retailer has determined that the monthly sales X of a watch are 150 units when the price is $50, but decrease to 120 units when the price is $60. Assume that the demand is a linear function of the price, find the revenue R as a function of X, and approximate the change in revenue for a 1 unit increase in sales when X is 141. So what are we doing here? Well, we know that we want to talk about the revenue. And we have a formula for revenue in terms of number of units times the price. But we don't know the price in terms of X quite yet. We're assuming here that the price is some linear function of the demand of X. But we need to determine what this particular function actually is. And they give us 2 points of data. We're told that we sell 150 watches when the price is $50, and we sell 120 watches when the price is $60. These basically are points on this line. We can go ahead and find m, the slope, using the slope formula. Remember, p here is playing the role of y, so the difference in y is up on top. And it doesn't matter which direction we subtract these, as long as we do the same direction here. We're going to take 60 minus 50. So down here I need 120 minus 50. Well, it's minus 150. Top is just 10. The bottom is negative 30. So we have a negative 1/3 as our slope. Then we can use one of these 2 points in order to find out what b is. So let's take this top one. If the price is 50, that corresponds to an x of 150. If we go ahead and solve this, we have b equals 50 plus, well, 1/3 of 150 is another 50. So actually, b is actually going to equal 100. So our demand equation here, p is equal, I'm going to go put the 100 in front, minus 1/3 x. And the revenue is just x times that. Revenue is 100x minus 1/3 x squared. Now we're going to calculate the differential of this. Remember, the differential, dr, is equal to our derivative. The derivative of this thing, it's not too hard to calculate here. The derivative of 100x is 100. Derivative of 1/3 x squared, well, I actually don't get to simplify that at all. It's just a 2/3 x. And it's going to be multiplied by dx. And so what they're asking for, so let me repeat their question. Find the revenue r as a function of x, which we just did. We did that here. and approximate the change in revenue for a 1 unit increase in sales when X is 141. So they're saying, assume that X is 141 and that we change our sales by 1 unit. That means we're changing X by 1. That means dx here is equal to 1. So X is 141, dx is 1. That means dr, if I plug those values in, we have 100 minus 2/3 of 141. They chose 141 because it is divisible by 3. It actually works out pretty nicely. And that's times 1. So this is 100 minus, and it turns out this is 94 when you take 2/3 of 141. So we end up getting 6. And that's essentially saying that our revenue changes by 6. It is a positive change, so it actually increases by 6 if we were to sell one more unit. That is what we're saying here. This is a way of saying that if we increase our revenue, or if we increase our number of units sold by 1, we should expect a $6 increase in revenue. Now, we could actually use our formula to get the exact increase in revenue. But in order to do that, we would have to calculate R of 141, the current revenue. We plug 141 in here. Now that does take a little bit of calculation to do. It turns out it's $7,473. That is our current revenue. And our revenue, if we sell one more unit, again, we have to go ahead and plug that in here. And this time it doesn't actually come out to be an integer like we did here. This came out to be a nice integer because 141 is divisible by 3 nicely. 142 actually isn't. But we get a value of 7,478.6 repeating. Or I guess if we assume that we're going to only be working in cents, we could go ahead and just say, let's just round it to 67. That means our actual delta R, not dr, our delta R is, say, 5.67. $5.67. So $6 isn't too far off from that. And really, if we are worried about just approximating anyways, then most of the time what we're really trying to do is predict what's going to happen. A prediction of an increase in $6 is probably a pretty good prediction when the actual amount will be a little bit, well, closer to $6 than it was to $5. And we can go ahead and maybe make a decision based off that prediction that won't be too far off. At least we know that the revenue would go up. That might be all that we need to know. So we want to sell more watches. Let's go ahead and do one more problem. Let's work on problem 41. This problem is about error. In exercises 41 and 42, use the following information. Given the error in measurement, so it's saying that delta x is going to be our error in measurement. The propagated error, this is what our delta y is. Can be approximated by the differential dy. So, of course, delta y is the exact value of the error. Dy is going to be our approximation. That's going to be a little easier to calculate. The ratio dy over y is the relative error. Now, technically, what they're saying there is wrong. It technically is based off of the exact error. It should be delta y over y. Basically, this is how much we are off percentage-wise. So, basically, if we're off, let's put it this way: if we're off by 1 when our expected value was 1, we'd be off by possibly 100% of what we were wanting. that could be a pretty big error. We could go anywhere from 0 to 2, and our estimated value of 1 would be just kind of meaningless at that point. But if we expected to get 100, and we had an error of 1, well, then we could be anywhere between 99 and 101. That's not too far off. I mean, relatively. It'd be an error of 1%. And that's what the relative error is saying. That if we have a big number for y, then a change in y needs to be relative to that to really account for what the error, how much of a percentage of error that we actually had. It's also going to say that the percentage error is the relative error in terms of a percent. Basically, you'd end up taking this number here, multiply it by 100, and that is a percent. Okay, now let's actually get into the actual problem 41. So these are just terms that they're going to be using here. In problem 41, they say the side of a square measured 6 inches. So we have some square. And has errors of 6 inches. Or, it's not errors. We have sides of 6 inches. But we just measured it. We think it's a square. We think it's we've taken a tape measure. We've measured the sides of it. We got a possible error because we might have just messed up a little bit. So our possible error, they tell us, is maybe plus or minus a 1/16 of an inch. We're relatively confident that we got it pretty close, but we might be off by a 1/16. We want to estimate the propagated error. So if we calculate the error, if we calculate the area of this based off of our measurements, we get one particular value. But if we had an error in the length of our sides, in the actual length of the sides, it could throw off the area of this square. And we want to know how far off could that error be? How close to the true area of this square are we? Well, we're going to make a function. What is the area in terms of the sides? Well, there's a reason why we use square for x times x. It's just the product of the two sides. So the area is equal to x squared. If x is 6, if 6 was perfectly correct, we take 6 squared, or 36. So that's what we assume that the area is based off of our measurement. But if the error is some plus or minus 1/16, which is, again, dx is the same as delta x, we take our differential. dA is the derivative. Derivative of x squared is just 2x. Then we multiply that by dx. And so dA is 2 times x. X is, we're assuming here, to be 6. Times dx. dx is plus or minus 1/16. That's the potential error. And if we multiply this out, we get plus or minus 3/4. Basically, our answer here, our 36 square inches, could be off by 3/4 of a square inch. Well, that means our percentage error, now let's just say our relative error, and then, like I said, this is delta y over y, but we're approximating delta y by dy. In this particular case, dA. So we're taking dA over a, or plus or minus 3/4 divided by 36, which is plus or minus Now, this would be 0.02 something. We're going to turn that into a percentage, so we're going to multiply by 100, so we get 2.083%. So we could be off from the true area of this by a little bit more than 2%, which might be good enough for our measurement. Now, I will also note here is that we can talk about relative error in the measurement itself. We could talk about what is dx over x. How much of an error are we possibly actually having here? In the whole 6 inches that we measured, if we have a possible error of 1/16 inch, then we're taking plus or minus 1 over 16. We're dividing that by the 6 inches that's what we measured. And we got plus or minus 1 over 96. Or if we turn that into a decimal, this is plus or minus 1.042%. It's really 0.01042 if we were just take 1 over 96. So we had a relative error in our measurement of approximately 1%. And that turned into a relative error in our area of approximately 2%. Really what's happened is we kind of doubled our area. And that kind of comes from the fact that we had a 2 here. You can do similar things if you're talking about the volumes of stuff. And there, because we were using the cube, it'll turn into 3 times the error. Stuff like that. It's kind of interesting that the multiplier out in front turns out to be the significant factor. But I don't really want to get too much into that. Just be aware that this is that this concept of differentials is very useful in a lot of applications. When you don't necessarily know exact values, or maybe you know you have an easy to calculate point on a curve, but you want to find this slightly more complicated point to calculate, but you don't want it to do as much work to find it. All that kind of stuff. That's the true purpose of these differentials. But this is all what we're really going to talk about them. There's a whole field of mathematics called numerical analysis that's all about making these sort of approximations using a lot of different techniques, not just calculus but other things as well. But this is kind of one of the starting points of that field. But this is the end of the chapter. We are not having a test just over this chapter. We will have a test at the end of chapter 4. So we'll be getting into chapter 4 next time. So I'll see you then.